Welcome you all to the 8th session of the Special Theory of Relativity in 5th semester BSc Physics. I am Sunil MH, Assistant Professor of Physics in Government First Grade College, Ranaganj. Here, today we are going to discuss a new thing which was a milestone in physics, that is Einstein's mass energy relation. Even if a student, a non-science student, also known Einstein because of this equation, that is E is equal to mc square. Is one of the most important and a milestone which created some history in physics. So let us see those things. The things which we require before going to the sessions here: frames of references, dynamics of the system, variation of mass with velocity, that is m is equal to m naught by square root of 1 minus v square by c square. That is, a mass is not a absolute thing. The mass of a particle will be varied according to the velocity of the particle. So here we are going to derive the Einstein's mass energy relation. As we know, force is the rate of change of momentum. That is, force we write into form, that F is equal to ma and F is equal to d by dt of mv, where mv is a momentum, the product and the velocity of the particle. Force can be written in this form also. Call this as equation 1. According to the theory of relativity, both the mass and velocities are variable. Before the introduction of a theory of relativity, it was considered that mass is a constant and it is the absolute physical quantity. But theory of relativity shows that as the velocity of the particle increases, its mass also increases. It was shown in the last session. And differentiating this thing, we get, that is, F is equal to m into dv by dt. Here m and b both are variable. Using chain rule, keep m constant, differentiate v with respect to t, and in the second term keep v as constant and differentiate m with respect to t, which gives F is equal to m into dv by dt plus v into dm by dt. The change in the kinetic energy when a body is displaced by a distance dx by applying the force F. We know that work done is equal to F into dx, force into displacement. But the change in kinetic energy is also considered as work done. So we can write a small change in kinetic energy, that is indicated by d into Ek. Ek is kinetic energy, is equal to work done, that is F into dx. So multiply equation 2 by dx, we get m into dv by dt into dx plus v into dm by dt into dx. Dx by dt is also velocity, since x is displacement. Dx by dt, here it is also velocity. So we can write dek is equal to m, that is m here, dx by dt is v and dv here, plus v dx by dt is v into v become v square into dm. Call this as equation 3. According to the variation of mass with velocity, relativistic mass equation, m is equal to m naught by square root of 1 minus v square by c square. Squaring and solving, we get, means square on the square on both sides, that is m is equal to m naught square by 1 minus v square by c square, and solving this equation we get mc square is equal to m naught c square, m naught square c square plus m square v square. Differentiating and solving, we get, so here it is taken, yeah, v is c is constant, that is velocity of light. Here v is a velocity of the particle, which is also variable. Now differentiating this equation, we get c square into dm with respect to is equal c square into dm is equal to mv into dv plus v square into dm. So we get 2 here, 2 will be cancels out in all the terms. We get this fourth equation. Now comparing this with equation 3, whereas the right hand side of the equation of 3 and 4 are equal, that is mv into dv plus v square into dm. So we can equate the left hand sides, that is c square dm and dek. So we can write equation as dek is equal to c square dm. Call this as equation 5. Now this shows that change in kinetic energy is proportional to change in mass. This shows that whenever the kinetic energy of the particle changes, its mass also changes. On integration with the range m0 to m we get. So integrating equation 5, in left hand side we can take limits of 0 to ek, and in right hand side we can take m0 to m. When m0, that is when a particle is at rest, kinetic energy becomes 0. When particle is at moving, its mass indicated by m, and kinetic energy become ek. Integrating equation 5, we get Ek is equal to mc square minus m naught c square. M naught c square is called the rest mass energy, and mc square is called total energy of the particle. Then the total energy of the particle, here we have written the kinetic energy of the particle. The total energy of the particle is equal to, that is E is equal to Ek, that is kinetic energy, plus m naught c square rest mass energy. Total energy of the particle is the sum of the kinetic energy and rest mass energy of the particle. Substituting for Ek, we get from the last equation we can substitute the value of Ek as mc square minus m naught c square. Here m naught c square, m naught c square get cancels out. So finally we get E is equal to mc square, which is a required Einstein mass energy relation. This relation suggests that mass can be converted as a energy, and energy can be treated as mass. It is mass of any particle or any body which has a mass m. Its energy is equal to c square times of that mass. This equation shows mass energy equivalence. This suggests that mass can be converted into energy. Here some of the illustration for mass energy equivalence. Let us take an example in the phenomena of pair annihilation or pair production of electron and positron combine and disappear. In their place, we found high energy gamma radiation. The radiant energy of gamma radiation is exactly equal to rest mass plus kinetic energy of the disappearing particles. This process is also reversible. Look at this picture. Here we have two particles. One is positron, indicated by positive sign plus, and other one is electron, which is indicated by minus. Here the two particles are going to be annihilate. Going to be annihilate means that they are going to be destroyed when positive antiparticle, where positron is the antiparticle of electron. When electron and positron combine together, that process is called annihilation or pair annihilation. When they annihilate, we are getting the energy in the form of the gamma radiation. This is one way. On the other way, when two high energy gamma radiation, here two high energy gamma radiation combining, this is called pair production. This is pair annihilation. Here is pair production. They are combining together to form positron and electron. This is shown in the other diagram also. Here the pair production, the two high energy gamma radiation combined together to form positron and electron. Here positron and electron combine together to form high energy gamma radiation. This is one of the example for mass energy equivalence. The next thing, the second example or illustration for that is the Einstein's mass energy relation can be verified in nuclear reactions such as fission and fusion processes. The reactions takes place in nuclear reactor and nuclear bombs. When an uranium nucleus is split up, the decrease in its total rest mass appear in the form of an equivalent amount of kinetic energy of fission fragment. Look at this picture. Here, uranium nuclei is bombarding uranium nuclei is bombarding with a neutron, then it moves to critical state or unstable, it become unstable nucleus, then it split into two fragments or products, one is krypton and the one is baryon, with the release of huge amount of energy and also the some of the neutrons. Here the kinetic energy of these product elements and their masses is equal to the total rest mass of the uranium nucleus and neutron. This suggests that a mass can be converted into energy. So in the other way, when uranium 235 is bombarded with a neutron, we get a critical nuclei here that is dividing into two product elements, krypton and barium, with the release of neutrons and also the energy. So here mass is converting to energy. Next, the reduction of relativistic kinetic formula to a classical formula. We have well known that kinetic energy relation, that is kinetic energy is equal to half mv square. That was a classical equation. Here somewhat we have kinetic energy equation, ek is equal to mc square minus m naught c square. So replacing m by m naught by square root of 1 minus v square by c square, and taking common m naught c square, we get inside the bracket 1 minus v square by c square whole power minus half minus 1. Here it is taken as common, so we get minus 1 here. Then for the particle which are moving with a velocity comparing to the velocity of light is very much lesser, then this part 1 minus v square by c square whole to the power of minus 1 by 2, using binomial expansion we can expand like 1 plus v square by 2c square plus etc. Neglecting higher order terms because we get small amounts, small values here that can be neglected, considering first and the second terms only and substituting this value here. 1 and 1 plus 1 and minus 1 cancels out, the remaining thing is v square by 2c square. So that can be written as kinetic energy is equal to m naught c square from here into v square by 2c square, which is equal to c square gets cancels out, remaining thing is 1 by 2 m naught c square, where m naught is the rest mass energy of the particle. This is the classical value of kinetic energy. So whenever the particle energy is very much less comparing to the velocity of light, we get the classical equation for kinetic energy. So when velocity of the particle reduces less than c, then the kinetic energy of the particle reduces to classical value. So let us see some problems here. If 10 kg of substance is fully converted into energy, how much energy is produced? So here we have given a mass m is equal to 10 kg. We are not considering the rest mass and relativistic mass. Just we are considering the mass of the particle. M is equal to 10 kg, and we need to find the energy of the particle. So using Einstein mass energy equivalence relation, E is equal to mc square, substituting for m is equal to 10 kg and c is equal to 3 into 10 to the power of plus 8. So multiplying these two quantities, we get 9 into 10 to the power of plus 17 joules. This is the energy released by 10 kg of mass when it is converted into energy. Let us consider one more problem. Calculate the rest mass energy of an electron in terms of electron volts. Here it is given, we don't have anything to see here. Just we should know the rest mass of the electron, that is the m naught, 9.11 into 10 power minus 31 kg. So here we need to calculate the rest mass energy of this electron. we know m naught value. So substituting m naught value in Einstein's mass energy equivalence, E is equal to m naught c square. Since we have written m naught here, because we need to calculate only rest mass energy. So rest mass energy, substitute this value, substitute the value of c, we get 8.2 into 10 power minus 14 joules. So we need in electron volts, not in joules. When we divide this by one electron, the value of one electron volt, that is 1.6 into 10 power minus 19, we get 0.51 million electron volts. This is the value of rest mass energy of an electron in electron volts and in joules. So we studied in this session here derivation of Einstein's mass energy relation, illustration for Einstein's mass energy relation, limitations of Einstein's mass energy relation, and numerical problems on Einstein mass energy relation. With this, I put an end to this session. Some of the reference books we can go through to study the Einstein mass energy relation in special theory of relativity are here. Thank you all.